So this starts off our next unit, which we call reactions. What we're going to talk about today is called balancing chemical equations and looking at chemical equations kind of as a whole. So there's a few symbols that we need to know, and we've seen these before, but just to formally introduce them. The first thing we already have seen before is an arrow. We use the arrow to separate our reactants from our product. So if you think back to some of the other units we were discussing, the arrow, it kind of acts like an equal sign in that it's separating your beginning of your reaction from your end. Now, if you have two or more reactants or products, we use a plus sign, just like in math, to separate them. So the plus sign versus the arrow have a clear meaning difference. It's there. And then another part of this, if you think back to a few units, we were discussing some phases of matter. One of the important things when we have a chemical reaction is you can kind of think of it as a recipe. So part of the recipe, you need to make sure you have the right type of ingredient. So if you've ever baked a cake or made frosting, there's certain types of ingredients that you need, otherwise your recipe won't turn out right. So this is kind of our way of doing that. So the S identifies a solid state. This script L identifies a liquid. We actually don't use liquids very often in this unit. This means I have a pure liquid, so it means it's a liquid of that. It's not something that's dissolved. It's just a pure liquid. So if you think of like ethanol, or if you think of something that's a liquid all by itself. So ethanol is a good example of that. G identifies the gaseous state. So those are kind of the ones that we've seen before. And AQ identifies an aqueous state. So if you think of aqueous kind of has aqua in it, which means water. So this is a solution. So this substance is dissolved in water. So often in our chemical reactions, we'll use aqueous substances more because we need it to be dissolved in order for the reaction to take place. So we often have aqueous. So a word that you might see associated with this is solution. A solution is usually, for us, is water. Water dissolves a lot of our substances, so we end up using it as kind of a place for most of our reactions. So a chemical equation represents a chemical reaction. You begin with reactants in your reaction and end with your products. So those are things that we've kind of seen before. Over to the next side, we have something called a diatomic elements. These are elements that cannot exist alone. So if you have this element in your chemical reaction, it has to be paired. Think of di meaning two from our naming unit. So there's 7 elements that do this, and we kind of have a fun way to remember this. Brinkelhoff, that includes all the elements. So if we had one of these in our chemical reaction, so let's say we had nitrogen in our reaction, which would be a gas, nitrogen would have to be paired. Now, if nitrogen is bonded with something else, it no longer has to be paired. It's only paired when it's alone. It just helps its stability for these substances. Most of these substances are gases, so that's also a contributing factor. You may notice that there's 7 substances here, and they actually make the number 7 on the periodic table with the exclusion of hydrogen. So nitrogen over to fluorine, down to iodine, as well as hydrogen. So the nitrogen to fluorine to iodine, that makes us 7, kind of a way to help you remember it as well. This is just to help illustrate that we have reactants, and then we could have a product, plus another product. So the plus sign separates things on the same side of the reaction. The arrow separates the reactants from the products. When we write a chemical equation, one of the things we have to check is we need to make sure that there's the same number of atoms on both sides of the equation. Just like a math problem. If we start with, 5 hydrogens or 5 water molecules, we have to have the same amount on the other side. So if we have 5 hydrogens on one side, we need 5 on the other. So here we have an example of water. You'll notice that it has hydrogen and oxygen, which are both diatomics, meaning they both are paired when they're by themselves. And they are both gases, which is what the G indicates, to form water, so H2O. So there's kind of 2 different things we have to balance. So from last unit, we have to make sure when we have ionic substances that we're balancing the ionic substance as well as balancing the equation. So I have this little table here that I like to use to help us balance it. This one's a little bit fancier than what I normally use. But just to kind of walk through the process, what you're going to do, you're going to take a look at you're going to take an inventory or you're going to count up how many of each atom you have on both sides. So we have 2 hydrogens on the reactant side, 2 oxygens, and then on the product side, we have 2 hydrogens and 1 oxygen. So right now, we have an unbalanced chemical equation. And eventually we're going to be using this in future problems, math problems. So we need to make sure we have this, that's where we're going with this. So we have to make sure we balance it for that reason. So what we're going to do, the only thing that we can change is the quantity of these specific molecules. We can't go through and change the subscripts. The only thing we can change is a subscript out in front. So for water, it gives me 1 oxygen, but on the reactant side, I have 2 oxygens. So what I'm going to do, in order to balance the oxygen, I have to put a 2 in front of the water. What that 2 will do is it's going to change the quantity of oxygen to 2 and change the quantity of hydrogen to 4. So now I have oxygen balanced, but hydrogen is not. So sometimes you have to mess up one of the balanced components in order to balance the equation. So the nice thing about this is there's usually multiple ways to do this, as well as multiple attempts are possible as well. So if it doesn't work out with one way, you can try a different way. So in order to balance the equation now, I have to balance the hydrogens, and we put a 2 in front of the hydrogen, and that changes it to 4. So because each hydrogen, there's 2, because it's a diatomic, we're going to, when we multiply it by 2, we end up with 4. So note, you can only multiply. You can never change the subscript because that would change the identity of the compound. So you might have been tempted to change water into something else. If you do, it's no longer water. So you can't change the chemical substances that you're working with. So these steps are what I just went through with the last problem. The steps, you don't have to follow them in order to balance the equation. This just makes you more efficient, so you'll balance it with less steps potentially. The only thing I wanted to point out is when you have a chemical equation, you want to leave anything that's a monoatomic, so if it's an element by itself, you want to leave that for the end because those are the easiest to balance. And this is something too you can always check when you're done. You can always check your quantities to make sure it works out. So taking a look at the next example here, this one has a few more substances, making it a bit more complex. So again, I'm going to start off by taking an inventory. So I have 1 hydrogen, 1 chlorine, and 1 zinc on the reactant side. And on the product side, I have 1 zinc, 2 hydrogen, and 2 chlorine. So right away, I see my hydrogen and my chlorine are not balanced. So what I would do is I would try to balance my chlorine, because chlorine is in 2 substances. Both hydrogen and zinc are monoatomic, they're by themselves. So I'm going to put a 2 in front of my hydrochloric acid. So that's going to change my chlorine to 2 as well as my hydrogen, and I end up balancing the equation. Sometimes you're going to see an equation that is already balanced without doing anything. Sometimes you'll need 1 number, sometimes you'll need numbers in front of everything. The other thing I wanted to point out, so when we don't write a number, it's assumed to be 1. If you go to do your vision homework, what you'll have to do is you'll actually have to type in a 1, and sometimes on your test you'll need to put a 1. So it's good practice to have those 1s, but they're not required officially. Let's take a look at the next example. We're getting a little bit more complex. So we're going to do the same thing. We're going to count up how many I have. So I have 1 aluminum, 1 calcium, and 1 sulfur on the reactant side. On the product side, I have 2 aluminum, 3 sulfur, and 1 calcium. What I would do, I would start by balancing my sulfur, because sulfur is bonded with something in both reactions. So I'm going to start there. So I'm going to put a 3 in front of my calcium sulfide. So that's going to change my number of sulfur to 3 as well as my number of calcium to 3. After doing that, I could pick either, it doesn't really matter. I'm going to put a 3 in front of my calcium and a 2 in front of my aluminum, and I have a balanced chemical equation.